In this brief recording, we're going to have a look at matrix equations and their solution. In particular, just going to give a very brief recap of direct methods, which were covered in mostly covered in Eng 1060. We'll also go through some of these in the workshops. So we're looking at linear systems here, and we're trying to find solutions to linear systems. But why would we be interested in this? I just thought I'd motivate this with a real-world example. And the example is understanding and visualizing three-dimensional volumetric data. So with various different MRI systems and CAT scanning devices, you can get really good high-resolution three-dimensional data, for example, of a skull. This data is multi-valued arrays that must be interrogated, filtered, decomposed, and then reconstructed into images like this. So, for example, we can look at the face, the surface of this individual, we can look at where the skull is, we can look at the shape and size of the brain, and with some techniques you can even look at the kind of brain activity that's going on. All of these things involve matrix manipulation and the solution of linear equations. So linear algebra and solving linear equations is extremely important in many applications. So basically, the simplest and the most common linear algebra problem you're trying to solve is a matrix equation that looks like AX is equal to B, where A is a square matrix, X is a vector of unknowns, and B is some right-hand side vector. There are several direct methods of solving this equation. The first one, the one that you might all certainly done in high school, is calculating the inverse of the matrix A. So if you can somehow calculate what A to the minus 1 is, then you can multiply this entire equation at the top by A to the minus 1. Get this equation here, and we know A to the minus 1 times A is just equal to the identity matrix, and that I times X is simply equal to X. So if we can calculate the inverse, we have the solution to our set of equations. It's simply equal to A to the minus 1 times B. Direct inversion, however, is usually very expensive, especially as the size of our systems gets bigger. The second direct method of solving this linear equation is Gaussian elimination, and this subject was covered in Eng 1060. Okay, we spent 2 lectures on Gaussian elimination, so I'm not going to go through it here. We do know it's very expensive. For n unknowns, it requires approximately 2/3 n cubed operations. And if you have 10 million unknowns, which is actually a typical size problem for fluid mechanics or structural engineering, this requires over 7 by 10 to the 20 operations. And if you see how long that would take on a fast PC, we're looking at 700 years. Even on the world's fastest supercomputer, if you could parallelize your code well, we're looking at over 200 hours. So Gaussian elimination is not efficient. A review of Gaussian elimination is covered in a lecture 3 notes on Moodle, and also in the review 3 Gaussian elimination.pdf. So I suggest you go back and have a look at that to refresh your memory. You might need to code it in a computer lab. There is also a set of equations that is known as the tridiagonal form, and I've slightly changed the nomenclature here for reasons that will become obvious in a minute. I've written the set of equations as AX is equal to D, and that's because I'm writing our matrix here as a system of coefficients, A's, B's and C's, which have this particular form. The diagonal coefficients are represented by B, the lower diagonal are represented by A, and the upper diagonal by C. This kind of system is quite obviously called a tridiagonal system because everything else above those diagonals and everything else below those diagonals is 0. And this system arises quite frequently. In this case, instead of using normal Gaussian elimination, we can use the efficient Thomas algorithm. And it turns out, instead of being of order n cubed operations to solve this system, the number of operations scales like the number of unknowns, so it's completely different. It turns out that the Thomas algorithm is exactly identical to Gaussian elimination, but because most of these elements are 0, in fact all of these elements under here are 0, we don't have to eliminate them. So we do away with a huge amount of elimination. We only ever have to eliminate the sub-diagonals, the A's. Then when we come to do the back substitution, each equation only involves one B and one C. The other advantage of the Thomas algorithm is because if the system is tridiagonal, the elements of the matrix A can be efficiently stored as three vectors, A, B and C. So we don't have to store all of these zeros. They're not needed. So we'll cover tridiagonal matrix inversion probably in one of the workshops. So for the Thomas tridiagonal algorithm, it requires order n operations, as I've already said. Now if n is equal to 10 million, that would take roughly 0.02 seconds, so 2 milliseconds. Compare that to 200 hours on a supercomputer. Significantly different. That's all I wanted to say on direct methods. We're going to focus in this unit on iterative methods.